Okay, so I decided it felt so weird to just start with those important inequalities without introducing them again. So I'll just introduce them quickly. But if you just watched the previous video, then you can skip ahead till here. Okay. So what I've done is I've written out all the notes so you don't have to wait for me to write them out. But it might be a good exercise to kind of pause as you need to and write down the notes and fill in your notes. So there are some important inequalities that we're going to use throughout the course. So I want to introduce them, and then some are going to be kind of more important than others, obviously. And so I do want to do an example at the end with the most important inequality or kind of the most applied inequality that we can use right away. So we're going to be talking about inequalities that relate to expected values. So in general, if G1 is a larger function than G2, then we expect the same of the expectation values. Okay, so, and we talked about why that is. Well, if we develop the expectation value of G of X, then how would we find that? Well, we would take the integral over all possible values of G of X times F of X with respect to X. And so one thing to remember is that F of X is that probability density function. So it's a probability, and so it has to be greater than 0, right? Technically between 0 and 1. And so F of X is always positive. And so if G1 of X is greater than or equal to G2 of X over the range of X values, and here we said, well, the context tells me that this range isn't referring to the range of the Y values anymore. That's usually what we call the range, right? But here we're talking about range just as in all possible values of X. So the range, or here, the possible values of X with F of X greater than 0. So, and it implies that the expectation of G1, if G1 is larger than G2, is going to be larger than the expectation of G2. And so what we said was, okay, well, if we're establishing that G1 is a larger function than G2, they would look something like this, right? And so for all values of X that we're considering here, the output of G at each point is consistently larger than G2. So then over this interval, we say that G1 is larger than G2. So the expectation value, or the expected value, usually we shortcut it to expected value, is the average of this function. And so it might be here. And so of course, if G2 is consistently lower, then of course the expectation of that function is also lower. Okay. So now I want to introduce these, there's some kind of 4 important inequalities that we're going to come back to at different points. Okay, so the first one is the existence of lower moments. Okay, and so if X is a random variable and we let M, so lowercase m, be a positive integer, right? 1, 2, 3, 4, 5. Then if we assume, right, suppose that the expectation of X to the power of M exists, right? So that's the mth moment, right? So we suppose that that exists. If K is a positive integer where K is less than or equal to M, then what does that mean? It means that the expectation of X to the K exists, right? And so the existence of lower moments is really just saying, if I tell you that the 4th moment exists and it's this, then you know that the 1st, the 2nd, and the 3rd moments also exist, right? And so knowing that, we can leverage that. Okay. We know that once we take derivatives long enough, right, often we'll end up at 0. So there are some where the moments kind of tap out, right? And so that's going to happen. But if we know that, the third moment exists, then we know that the first and the second moments also exist. Okay. So that's fair enough. Markovs inequality. If we let u of x be some non-negative function of the random variable x, then if the expectation of the function u of x exists, then just kind of as a rule, for every positive constant c, right, the probability that u of x is greater than or equal to c is less than or equal to the expected value of u of x over c. Now, we're not going to talk about this one now, but it's just good to have in our back pocket, and I'll point you back here when we talk about it and when we need it. Okay, so this one we're just kind of stating, and then we're parking lotting it. The third inequality is one that I want to do an example of because it's kind of a fun inequality, and it can be pretty useful. And so Chebyshev's inequality, fun to say, fun to do, says that if we let x be a random variable with finite variance sigma squared, what does that mean? It means that, well, sigma squared, remember, is the variance. The variance is the second moment minus the first moment squared. So this implies that the first moment exists, right? That the mean E of x exists, right? And that's from the first inequality, right? And it also implies that the second moment exists, right? But if the second moment exists, then we know from that first inequality, right? This one here, the existence of lower moments. So if I tell you that the variance exists and it's finite, then you know that the expected value of x, the mean, also exists. Right? So then for every k greater than 0, k is not necessarily an integer in this case. And I'm going to emphasize that by using a k that's not an integer. Then we can have this weird probability. So the probability that the absolute value of x minus mu is greater than or equal to k, that constant k times sigma, okay, is going to be less than or equal to 1 over k squared. That sounds weird, and that's why I want to do an example to show you what it means. Or equivalently, if we want to talk about, instead of greater than or equal to k sigma, we could talk about less than k sigma, right? That's going to be greater than 1 minus the previous one, 1 over k squared, right? And so here I have a little note that we're going to do an example after the final inequality. There are, of course, lots of other inequalities, but these are the ones that we're going to focus on for now. Jensen's inequality is another one of those inequalities that we're just going to mention, and then we're going to parking lot it until we need it. Okay, so the one to focus on from this section is definitely going to be Chebyshev's inequality. Okay, but if phi, so phi is Greek letter phi, if phi of x is a convex function, so convex functions look like this, right? Where if you connect any 2 points on the curve, then that line is always going to be above the function. That's the convex function. So if phi of x is a convex function over the set of possible values of x, which has a finite mean E of x, so that's an assumption that we're making, then phi of the expectation of x is less than or equal to the expected value of phi of x. That's weird, but we're just going to parking lot that and keep that in mind. So essentially what happens is, in my mind, at least when I look at this, I say, okay, well, the function on the expectation is less than if I take the expectation of the function. Okay, so going back, let's review Chebyshev's inequality to see kind of what's going on here. We're going to use it to establish an upper bound for probabilities, right? So it's not going to give us the probabilities. And there are situations where even like the one that we're about to do, where calculating the probability exactly might be a little bit rough. It might be really time consuming or computationally expensive. So then it might be helpful to just say, okay, well, I know from Chebyshev's inequality that it's not going to be more than this, right? So it establishes some upper bound for the probability. So let's scroll back there and see here what it looks like. So we have some random variable x with some mean and some variance. So it has to exist. Okay, then for every k, as long as k is positive, right, greater than 0, then we can find that the probability that x minus mu, remember mu is known, right? So we're going to have some value for mu. The probability that this absolute value is greater than or equal to that constant times the variance is going to be less than or equal to 1 over k squared. Right, and so the largest possible probability that we can get is 1 over k squared. Okay. Or we could use it the other way around, but let's focus on this first one. They're the same. So then let's consider just a kind of an easy example, not too easy, but we're going to let x have a uniform PDF. So it's going to be a continuous function, which means we need to practice our integration skills. And so f of x is 1 over 2 root 3. So it's this uniform distribution. And it's on x from negative root 3 to positive root 3. And it's going to be 0 anywhere else. Okay. So here, kind of pre-baking it, and I encourage you to try to find the mean and the variance, right? You can generate the moment generating function, or you can find e of x and e of x squared just by using the PDF, right? And integrating the PDF times x or x squared, and then constructing your mean and your variance. But I'm going to leave that for you to practice. But after some work that we will skip here, cheeky, we find mu equals 0 and sigma squared equals 1. So if you want to pause it here to try to find those, that would be a good exercise. Right? But I'm going to leave it for now. Okay. If we pick some k is 3 over 2, let's say, right? It doesn't have to be an integer, so that's why I'm showing here 3 over 2 is not an integer. Then we can find the exact probability, right? And so what we can do is we can find the exact probability, and then I want to compare it to the upper bound. Okay, so here, if I set up this exact probability, I'm going to have the probability that x minus mu, but remember mu is 0 here, so I'm going to substitute mu equals 0 here, is greater than or equal to k. K is 3 over 2 times sigma, which is 1. Okay, so let me just draw those lines here. Like this, and like this, and like this. Okay. So then when I rewrite it, it looks all simple, right? I want the probability that the absolute value of x, remember the absolute value of x is kind of this v function. I want the probability that that absolute value of x is greater than or equal to 3 over 2. Okay. That's going to be the same as, so greater than or equal to means I'm on the upper end of the curve, whatever the curve looks like. In this case, it's a uniform distribution. And so now I want 1 minus the integral from -3/2 to 3/2, right? Because I want it, I want the absolute value of x to be greater than or equal to 3/2. Okay? And so 3/2 is kind of that cutoff, and then I want past that point. And if I do 1 minus the area between those 2 points, then I get the area that I want, right? So what we can do is, let's see if I can map this out here. Maybe scoot this over a little bit, right? If we're talking about a uniform distribution between -√3 and √3, then this here is going to be at 1/2 √3. Right? So if I want the probability that the absolute value of x is greater than or equal to 3/2, what could I do? Well, maybe not use that color. So here, -3/2, +3/2. If I'm looking for this area, right, the probability of being beyond those 2 points, right, I'm looking for this area. That's going to be 1 minus the area between those 2 points, right? So this area is 1 minus this area. How weird is that? Pink question mark is 1 minus a green question mark. You had to be here. Hopefully it makes sense. I don't know. Makes sense to me. Okay, so and if you don't want to visualize it, you don't have to. I just want to show you where it came from. Okay, so now, right, what we're going to do is this probability, we can rework it like this because that's an easier integral to do, right? Just 1 instead of, well, what would it be? 2, right? Could add the 2, could do this side and then add it to this side. No, thank you. Okay, so if we integrate, what's nice about this function is that it's uniform, right? And so integrating a constant is, we can do that all day, right? It just becomes x. So that's great. So this becomes, and I'm gonna just bump it over just a little bit to give myself a little bit more room here. And I wanted to write this out together in case I wanted to point anything out. So I didn't want to have these pre-written, so you'll have to bear with me. So it's going to be 1 minus, and once we integrate, and so I'm assuming you're okay with integrating a constant, we get, okay, fine. No, I'm just going to do it. 3/2 is the upper bound over 2√3 minus the lower bound, -√3/2 over 2√3. I can simplify this. There's a couple of ways, depending on how many steps you want to take here. I always like to do way more steps than you have to, just because it helps me solidify what I'm doing, right? I don't want to look back and be confused by something that I wrote. So I'm going to treat this as a fraction over a fraction, right? 3/2 is definitely a fraction. 2√3 I could write as 2√3/1, right? I use that trick very often. So 3/2 over 2√3/1. When I flip and multiply to combine into one fraction, I'm going to end up with 1 minus 3/2 times 1/2√3. If I do the same thing with the other side and also combining my negatives, my minus and my negative, I get plus 3 over 2 times 1 over 2 root 3. Okay. I see a 3 and I see a root 3, so I'm going to rewrite 3 as root 3 times root 3, right? That's usually how I end up canceling or moving square roots around. So here I get 1 minus root 3 times root 3 over 4 root 3 plus, I'm going to do the same thing on the other one, root 3 times root 3, 2 times 2, that's where the 4 came from, 4 times root 3. So now I'm ready to cancel these root 3s because, oh, maybe I should be consistent in which ones I cancel. It doesn't matter. Right, but now I have root 3 over 4. So what next? Now I'm going to put this on the next page here. So this becomes 1 minus root 3 plus root 3 both over 4. So a common denominator of 4. So I'm going to combine those here. Root 3 plus root 3 over 4. That's 2 root 3, of course, which if you're feeling comfortable, you could just cancel with one of the 2 times 2 down here to make 4. But I'm going to show what happened because why not? 2 root 3 over 2 times 2. Now I can cancel. So I have 1 minus root 3 over 2. Okay. 1 minus root 3 over 2. I could rewrite it as something fancier, right? I could put 1 over a common denominator of 2. So I could rewrite 1 as 2 over 2, but I would still have 2 minus root 3 over 2. And I don't really think that I gain anything from that. So I'm just going to leave it here. Okay, so here, this becomes 1 minus root 3 over 2. This is the exact answer. Maybe make it look like I wrote answer. Not sure what it looked like. There. Okay. The approximation here, if I am dealing with decimals, I have it here, or approximately 0.1339745962. I am just copying that out from my page here, so I'm just going to double check here. And hopefully I did it right the first time. Who knows? 9745962. Okay. If I wrote it down on the page right, then it's right here, but who knows? So that's our exact probability, right? And so now what I want to do is I want to compare it to what would I get if I just use the upper bound, right? To figure out, okay, it's going to be no more than this value. Okay? And so by Chebyshev's inequality, this probability has an upper bound of 1 over k squared, right? And so by Chebyshev's inequality, this probability has the upper bound 1 over k squared, which is 1 over, remember k, we decided we were going to try 3 over 2. So 3 over 2 squared is 1 over 9 over 4, right? Bring that square inside, but then I've got a fraction over a fraction again, right? And then so I need to flip and multiply. And so I get 4 over 9, which is approximately, well, it's 0.444 repeating, So without having to do this huge calculation, right? This one that we just spent some time working on, what we could have said, if we didn't need the exact probability, if we just needed to have a rough idea, then what we could say is we could say, well, it's going to be no more than 0.444444, right? So that's a good jumping off point. Notice that 0.13397 blah 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 is quite a bit less than 0.4444, but that's what makes it an upper bound, right? It's not going to be any more than this. And I'm noticing that one of my 9s doesn't quite look like a 9 here. Feels important that it does. Okay, and so notice that the exact probability is quite a bit less, very technical, quite a bit less than 0.444 repeating, but since 0.13 all round to 3 decimal places, or 4, I guess, is less than 0.444 repeating, 1 over k squared is indeed an upper bound, right? It just chops it down so that we're not just, oh, probabilities are between 0 and 1. That's not very helpful. Right now we're saying, okay, we don't really know what it is, but it's no more than 0.44. Okay. That can be useful. So 1 over k squared is indeed an upper bound. Nice. Okay. Nice work. That finishes chapter 1. I'm excited. I hope you're excited. And so nice work. I'll see you next time.